Several of the exercises on right triangle applications involved a figure similar to the one shown here. So for a lot of the problems where we solved right triangles in Chapter 2, we were dealing with a figure like this. So what they're implying here is that there's an array of real-life applications where you deal with a geometrical figure like this. So we've got these two right triangles here, one inside of the other, and then this oblique triangle here, okay, in which angles alpha and beta and the length of line segment AB are known, and the length of side CD is to be determined. Use the law of sines to obtain x in terms of alpha, beta, and d. So in a lot of cases, you'll have this kind of figure here, and you know alpha, beta, and d, but you don't know x. So they're asking us to solve for x in terms of, you know, the unknown x parameter in terms of these known parameters using the law of sines. Okay, so let's use as some notation here. So angle D is this entire angle. Okay, so let's think about that. And then like angle B is this entire angle, and angle A is just alpha. So, okay, with that, we can think about how we've got this outer right triangle here, and we know that the acute angles of a right triangle are complementary. So angle D is going to be equal to 90 minus alpha, you see? Because alpha plus 90 minus alpha plus 90 is equal to 180. All right? So, okay, what else? We can do the same idea with this right triangle. We can see that this is 90 minus beta, right? Okay, now we can see that, so if D is 90 minus alpha, and this is 90 minus beta, then if you did 90 minus alpha minus 90 minus beta, you'll get this angle. Let's see if that gives us anything. 90 minus alpha minus 90 minus beta. So 90 minus alpha minus 90 plus beta. That's beta minus alpha. So this is beta minus alpha. Okay. Now let's do the law of sines on this outer right triangle here. And so I want to do the law of sines because you might say, well, why don't we just do like regular trig functions? Well, because it will be easier to relate alpha and x to this side length here with the d in it. I want to take out, I don't want to be bringing in this hypotenuse here if I don't have to. So let's do the law of sines. So sine of alpha over x. So normally I would have to say with just sine alpha would be x over hypotenuse, right? So, I mean, we could still in a roundabout way use regular trig functions. Like we would get, like we could use tangents and stuff, but this will be easier. So, okay. Now we can say that, so this is equal to sine of d, which is 90 minus alpha, but sine of 90 minus alpha is cosine alpha. Right? That's a cofunction identity. So we could just change this to cosine alpha over, and then d plus bc. So again, we did sine of alpha over x is equal to sine of 90 minus alpha, which is cosine alpha, over this side length. Okay. Now let's do the law of sines on this right triangle. So we can say that sine of beta, and again, I don't want to use regular trig functions because sine of beta is x over this length. I don't want to deal with this length if I don't have to. So sine of beta over x is equal to, and then sine of 90 minus beta is going to be just cosine of beta over BC. Okay, so now let's solve this for x. So x cosine alpha is equal to d plus bc sine of alpha. So x is equal to D plus BC sine of alpha over cosine of alpha. Okay, now here we've got x, solve for x here, x cosine beta is equal to BC sine of beta. So x is equal to BC sine of beta over cosine of beta. Okay, now let's set these two equal to each other. Okay, now we've got alpha and we've got beta and we've got D in here, which we're okay with because that's going to be part of our final answer. But we don't want to have BC in here, so let's solve for BC. Because we can solve for BC and then substitute for BC. If we can solve for BC in terms of alpha, beta, and D, that's what we want to do. So, okay, BC cosine alpha sine beta, cross multiplying, is equal to D plus BC sine alpha cosine beta. Okay, so we've got BC cosine alpha sine beta is equal to D sine alpha cosine beta plus BC sine alpha cosine beta. Okay, so now subtracting BC sine alpha cosine beta from both sides, what we get is, so we can factor out a BC over here, so we'll get cosine alpha sine beta minus sine alpha cosine beta. You see? We subtracted BC sine alpha cosine beta from both sides, and then we factor out this BC. D sine alpha cosine beta. Now, okay, does this match up with a sum or difference identity for sine or cosine? Okay, let's see. So if it's going to be anything, it's going to be a sum or difference identity for sine. So we've got sine alpha cosine beta minus cosine alpha sine beta is equal to sine of alpha minus beta. So let's see how that matches up here. We can write this as, let's see, let's do sine beta cosine alpha and then we want to put this as cosine beta sine alpha. And then we can see the form, how the forms match up. So that gives us, this would be sine of beta minus alpha. That's what sine beta cosine alpha minus cosine beta sine alpha is. Sine of beta minus alpha. Let me do this. So BC sine of beta minus alpha is equal to D sine alpha cosine beta. Okay, so now BC is equal to D sine alpha cosine beta over sine of beta minus alpha. Okay, great. Now, if we look here, look back at these x values, like we're trying to solve for x as a function of alpha, beta, and d. So what we could do is just, here's the simplest form where we could just plug BC in here. And we're left with just betas, alphas, and lowercase d's. So, okay, let's just plug this BC in here. So we've got, let's see, D sine alpha sine beta cosine beta in the numerator, and then cosine beta sine beta minus alpha in the denominator. Okay, these cancel, and so we're left with x is equal to d sine alpha sine beta over sine of beta minus alpha. And there we go.